Okay, welcome class to Physics 203, class number 13. This class is on the Heisenberg uncertainty principle, which is something that I'm sure you've all, well, I think many of you have heard about and that we've been building up to in our study of quantum physics. And it basically expresses, as a preview, a limitation on our ability to know the position and momentum of a given particle at a particular point in time, which is in contrast to our classical picture where we can precisely locate the position and the momentum of a particle, of any particle at any point in time. So let's talk about waves and wave packets, because this is going to figure into our derivation of the Heisenberg uncertainty principle. So a continuous wave, periodic wave, can be represented in the following form. Psi is just a symbol. You might have used Y before in a previous class, but psi of x and t is an amplitude times some sinusoidal function of kx minus omega t plus phi. And let me just remind you, in case you don't remember, you might be more familiar with wavelength and period, but k is the wave number, which is 2 pi over lambda, and omega is the angular frequency, which is 2 pi over the period, or 2 pi times the natural frequency. And then phi here is just a phase to adjust the to shift the origin of the continuous wave. So this function psi could represent any number of waves, water waves, sound waves, but let's concentrate on it representing electric field amplitude. So here is an electromagnetic wave, and it's traveling in this direction from left to right, and it's oriented in the vertical direction. And so the psi here would represent the amplitude of the electric field as we move along x, and then of course as time changes the electric field will move along, and so it's both position and time dependent. So however, so how do we interpret this psi for electric fields? Well, from the experiment for two-slit light diffraction that Thomas Young did first back in the early 1900s, recall that we have incident light waves and two slits separated by a screen, separated by a barrier, and light incident on a screen here. And it turns out that if we slow down or make the light much less intense, we can actually, and use modern detectors, we can actually see the individual particles of light, photons, building up. Okay, so this is after 20 counts, 100 counts, 500 counts, 4,000 counts. And we can see the interference pattern gradually being built up out of a seemingly originally random pattern. So what that tells us is that at these positions where there's a large electric field amplitude, according to our wave analysis, there's a large, strong chance of finding, of detecting a photon, okay? So that suggests that if we want to represent a particle, we need a wave packet that's localized in space, because a particle is localized, at least to the greatest extent we possibly can, localized in space. It's not spread throughout space. So a continuous periodic wave here would represent uniform probability through space, since the electric field magnitude would continue on and on and on and on, and so there'd be a chance of finding a photon anywhere. But how would we represent a localized packet of energy, like, for example, a photon? So to do that, we're going to do that in a couple of steps. First, we're going to kind of build up. We're going to start with two waves and define things called the phase velocity and the group velocity, which are going to be key to understanding the propagation of these so-called packets, these wave packets. So we start with a superposition of two waves, and here they're black dotted and black dashed. So you can see they have not quite the same wavelength or wave number. They have the same amplitude, but not quite the same wave number, nearly the same wave number, and so nearly the same angular frequency, omega. And then when we add them together, we get this blue wave, this light blue wave, which forms sort of an envelope around the two waves. So the mathematical analysis, remember this was our form for the wave. Psi of x and t is an amplitude times sine of kx minus omega t plus phi. We can set phi equal to, let's see, we can set phi equal to pi over 2 and convert this to a cosine of kx minus omega t. So phi is just a phase factor which shifts the origin of our wave. So in our analysis, we have these two waves, psi 1 of x and t and psi 2 of x and t, and we have the amplitude times cosine instead of sine, because we've set this phi properly, of k1 x minus omega 1 t plus k2 x minus omega 2 t. Notice k1 and omega 1 are different from k2 and omega 2 because they have nearly the same wave number, but not exactly the same. And then through some trig identities, which I won't get into, you can combine these two. So there's trig identities for the cosine of a plus b, and there's a series of steps here which I don't want to digress on, but we can write this as 2a times the cosine of 1/2 of k1 minus k2 x minus 1/2 omega 1 minus omega 2 t times the cosine of 1/2 k1 plus k2 x minus 1/2 the 1/2 omega 1 plus omega 2 t. Okay, so this, from this step to this step, is applying several trig identities. But we're not concerned, I'm not too concerned with the mathematics, but with the physical meaning. And k1 minus k2 we'll call delta k, that's the difference in wave number. And omega 1 minus omega 2 we'll call delta omega. And then k1 plus k2 over 2 is just the average of the two wave numbers. And omega 1 plus omega 2 over 2 is just the average of the two frequencies. So this looks just like, if we think of this first term underlined here as an overall amplitude, it looks like something times cosine of kx minus omega t, where k average is close to k1 and k2, okay? So this right here, 2a times cosine of this term here, is this blue envelope, okay? So it's an oscillation in the amplitude, which was constant originally. It's an oscillation in the amplitude. And apparently that amplitude moves because it has a cosine dependence in x and t, and it moves with what's called the group velocity, which would be the coefficient of the time over the coefficient of the position, so delta omega over delta k. Meanwhile, inside the envelope, the combined components move at what we call the phase velocity, v phase, omega average minus, over k average. Okay, so in general, wave velocity can be written as omega over k, and we have the group velocity, which defines this moving envelope of the combined waves, and the phase velocity, which defines the individual component waves moving along within the overall this overall group envelope. And there's a nice illustration of this in the textbook, which involves dropping a rock into water. So if you drop a rock into water, you get a splash, and you get a sort of a disturbance which moves outward, and that's represented. The center of the disturbance is represented by these x's. Okay, so you can see the x's just move out very uniformly. But when a new wave is formed, because the rock has disturbed the water, you can see that new wave is represented by these, alternately by these arrows and these dots, actually moves at a faster speed than the center of the disturbance. Okay, so in this case, the group velocity would be the velocity of these x's. That's the velocity of the whole group of waves that are moving out, whereas the phase velocity of this particular wave would be greater. In fact, it's greater by looks like a factor of 2. The phase velocity is twice the group velocity here. So that's just an everyday example. Okay, so for wave packets, we're concerned with the group velocity, because we want to know the velocity of this overall group as it moves through space, not the individual component waves which are making up the group. Okay, so that was with 2 waves. Now it turns out to make a something which is this is not localized in space. This would continue onward, and so we would not get a particle like a photon which is localized in space. So we need to superpose many waves in a Gaussian wave packet. So 2 wave numbers give an infinitely long train of wave packets. We need many wave numbers k to get a single wave packet. And the way we do this is just adding up. Instead of adding up 2, a1 cosine of k1 minus omega t plus a2 cosine of omega 2t, we add up a series where a sub I would be a1, a2, a3, k sub I would be k1, k2, k3, omega sub I would be omega 1, omega 2, omega 3, and so forth. And this is actually called a Fourier series, which you will be covering later on in Physics 270. It's just basically a sum of cosines, or could be sines, but in this case, cosine is a Fourier cosine series with each wavelength or each wave number having a different amplitude. And that can be generalized to not just a discrete sum, but as you know from calculus, a sum, if we make it fine enough, can be turned into an integral. And so we can define the wave packet as an integral of a continuous amplitude as a function of k times cosine of kx minus omega t dk. And that's called a Fourier integral. And if you may have time to get to Fourier integrals in Physics 270, but I'm sure you'll at least get to see physics Fourier series. So an important example of this is called a Gaussian wave packet. And it evolves in time as psi of x and t, so it would be a certain combination of cosines weighted appropriately, and we'll see what that weighting is in a second. And I'm showing it dynamically. It turns out that this is the wave packet. As you can see, it starts out, I'll wait for a second, it starts out more localized and gradually spreads out. And that's because in this medium, it's called a dispersive medium, the individual components move at different, the individual wave numbers or wavelengths move at different velocities, and so the wave packet tends to spread out. Just an interesting side note there. But for simplicity, we're going to look at t equals 0, so at the start. And in that case, we can represent psi of xmt as psi of x of 0, t equals 0. So it's just a function of one variable x. And psi of x would be an amplitude times e to the minus delta k delta. It turns out for a Gaussian wave packet, e to the minus delta k squared times x squared. So that would be the this would actually be a Fourier integral, not a Fourier series, as I said before. I apologize. This would be a Fourier integral. We're summing up over, well, it would be a Fourier integral because it's a continuous function of a Gaussian, which is e to the minus x squared with a certain width, times cosine of a dominant frequency, a dominant wave number k0 times x. So let's take a look graphically at what that looks like. The Gaussian here has a width delta k. So that's because the width is in statistics of a Gaussian is sigma squared, and sigma squared, well, it's normally x squared over a length squared, but since delta k is 1 over a length, it's the 1 over the length. The length 1 over the length squared is just delta k squared. So the standard deviation of this Gaussian is delta k, which appears here. And then here is the envelope, and we're taking a, just for convenience, equal to 1. E to the minus delta k squared delta x squared. So this is e to the minus delta k squared delta x squared. And then inside we have the cosine of k naught x. So we can see that we have this wave packet where the outline is given by the Gaussian shape, e to the minus delta k squared delta x squared, and the individual oscillations are given by the cosine of k naught delta x. And we can express the width of the wave number by this standard deviation of the Gaussian delta k, and we can express the width of the wave packet as the width, as the characteristic distance through which the wave packet falls to about roughly half of its original height. It turns out to be 1 over e of its original height, but essentially 1 over half. And using some mathematics, which again, I want to get across the concepts here and not get into the mathematics, it's possible to show that delta k times delta x is equal to 1/2, okay? So what does that mean? That means if we make delta k smaller, if we make a tighter width of wave numbers, that's going to make a wider spread of positions, okay? Because if delta k is smaller, we're going to have to go to a larger delta x to get the same drop in this term here. So delta x would get greater. And vice versa, if we make a wider delta k, then we would get a tighter distribution of delta x. Okay, so the wider the spread of wave numbers included, delta k, the narrower the position distribution. Okay, and this is going to be a key to the Heisenberg uncertainty principle. So how do we connect this? So far, this is just the mathematics of waves. How do we connect this to quantum physics? Well, it's via the de Broglie relation, which we learned about in the previous class. Recall the de Broglie relation that P, the momentum of a quantum particle, is equal to h over lambda. And then we'll just do a little manipulation here. We'll divide h by 2 pi and multiply lambda by 2 pi. So we're just dividing and multiplying by 2 pi. And we get h over 2 pi times 2 pi over lambda. But h over 2 pi is h bar, and k, 2 pi over lambda is our wave number k. So we have another way to express the de Broglie relation. H over lambda is h bar times k. Okay, so remember, our goal is to represent a particle like an electron with a wave packet, so that we can have it localized in space, as suggested here. Here's the electron, and it's moving along in space. So we found for a Gaussian wave packet that delta k times delta x was equal to 1/2 on the previous slide, or we quoted that result. So now solving for delta k here, we have delta k would be delta p over h bar. Since p is h bar k, dividing by h bar, we get k is p over h bar. So delta k would be delta p over h bar. Delta x is equal to 1/2, or multiplying through by h bar, we get delta x delta p is equal to h bar over 2. Okay, so now the Gaussian wave packet is in some ways an optimal wave packet. It gives the smallest possible value for the product between delta k and delta x. For differently shaped wave packets, like Lorentzian, we used a Lorentzian earlier, or some kind of double exponential wave packet, the product delta x delta p is actually can be a bit larger. So that leads us to say that delta x delta p is at minimum h bar over 2. That's realized by the Gaussian wave packet. And in general, it's greater than or equal to h bar over 2. And that, my friends, is the Heisenberg uncertainty principle. It says that the spread in x of a particle times the spread in momentum is greater than or equal to Planck's constant, reduced constant, over 2. So this places a fundamental limit. So the mathematics that we've used to build wave packets out of plane waves, delta k, delta x equal 1/2, combined with the de Broglie relationship relating the wave number to the momentum, has led to a limitation on our knowledge. So this is a schematic of combining plane waves into a wave packet here, which says, again, that the more accurately we know the position, that is, the lower delta x is, the less accurately we can know the momentum. The larger delta p would have to be in order for the product to be greater than or equal to h bar over 2. And vice versa. The less accurately we know the position, the greater delta x, the smaller delta p, the better we'll know the momentum. And just to emphasize, this is in contradiction to classical physics, where we can know there's no spread in position or spread in momentum. A given particle, we can nail down its, in principle, its position and momentum to arbitrary accuracy. Okay, so this is the Heisenberg uncertainty principle. And just to emphasize one more time, it comes because we believe that things have a wave nature, and to represent a particle as a superposition of waves, we need to build them up out of plane waves, and the mathematics of that says that there's a limitation on the spread of plane wave numbers that we need to get a certain spread in positions. So needless to say, the interpretation of this and the debate between the big scientists of the time was quite vigorous. As I said, a vigorous debate went on between Einstein and Bohr and others in the early to late 1920s, leading to many thought experiments, not limited to the one that I'll show here. Here is electron diffraction going through two slits, which would normally cause an interference pattern. But Einstein imagined if we had a source of light here so that we could shine it on the electron and determine whether it went through this lower slit or this upper slit, that we would we could gain more information about the we would simultaneously know the electron's momentum and its position. But unfortunately, if we do that without the light, we get wave-like behavior and the interference pattern, the familiar interference pattern. And with the light, it turns out that the photon coming from the source of light scatters from the electron and shifts the electron's momentum and the direction, changes the momentum of the electron in just such a way as it smears out the interference pattern here. So we don't get any interference pattern. So it seems that we either get wave-like behavior or particle-like behavior depending on how we interact with the system. And this led Bohr to, Bohr was able to resolve this and a series of thought experiments that Einstein and several others proposed with his principle of complementarity. That is, which he said, it's not possible to describe physical observables simultaneously in terms of both particles and waves. So we have to look at, depending on the situation, we have to treat something as a wave, generally when it's propagating through space freely or through matter freely. When it interacts with atoms or with other particles, we have to look at it as particles. And this is the wave-particle duality, which seems to be here to stay. And I'll just wind up with this picture emphasizing the fact that in the photon experiment, the waves going through the going through the slits dictated the probability of finding the photons, but with low enough intensity, we saw the interaction with the atoms of the detector photon by photon. Okay, so some really interesting stuff here, and I hope you've enjoyed it, gotten a greater appreciation of the Heisenberg uncertainty principle, and I will see you in class.